In this video, we'll take a look at degree sequences and the Hebel-Hakimi theorem. Now, what is a degree sequence? The degree sequence of a graph is the finite sequence of degrees of all its vertices. So, let's say you have a graph. You find the degrees of all the vertices and then you write them as a sequence. So, that gives you a degree sequence of a graph. Graphic sequences. A finite sequence of non-negative integers d1, d2 up to dn is said to be graphic if there exists a simple graph G with the vertices v1, v2 up to vn such that each vertex vi has the degree di. In simple words, a sequence of non-negative integers is called graphic if it is the degree sequence of some simple graph. Now, two necessary conditions for such a sequence to be graphic are: the degree of each vertex should be less than the total number of vertices. This is necessary for a simple graph because in a simple graph there are no loops and a vertex cannot have an edge connected to itself. Thus, the maximum degree of any vertex is the number of other vertices it can be connected to, which is n minus 1, where n is the number of vertices. The second condition is the sum of the degrees of all vertices should be even. This is by the handshaking lemma. Now, however, these two conditions together do not ensure that a sequence will be graphic. It is easy to find the degree sequence of a graph, but finding whether a degree sequence is actually a degree sequence of some graph is harder. Okay, so there is a constraint on the vertex degrees of a simple graph. The degrees of vertices have to repeat, or in other words, all the vertices of a simple graph cannot have a distinct degree. Proof: assume a graph with n vertices where each vertex has a distinct degree. To assign each vertex a distinct degree, we need a set of n numbers. If we start vertex degrees from 1, then it will go up to vertex degree n, but the graph is a simple graph and it rules out the possibility to have self loops and parallel edges. So therefore the degree sequence should be 0 to n minus 1. Now there is a problem here as well. A vertex with degree 0 means that one of the n vertices is disconnected, whereas a vertex with degree n minus 1 means that a vertex is connected to each one of the remaining n minus 1 vertices. Now this is impossible because one of the vertices is disconnected. Therefore, the maximum degree possible for the most connected vertex should also be n minus 2. So both the statements cannot be true simultaneously. It is a contradiction. So therefore, our initial assumption is incorrect. Okay. Therefore, we have proved by contradiction that all the vertices cannot have a distinct degree in a simple graph. So let's take a look at some examples. Is the sequence 2, 2, 3, 3, 3 graphic? It is not, because number of odd degree vertices cannot be odd. Or in simple words, if you take the sum of all the degrees, it comes out to be 1, 3, 13, which is an odd number. So it cannot be odd. Second one, is the sequence 1, 2, 3, 4, 5, 6, 7 graphic? So first thing to note over here, there are 7 numbers in this sequence. So 7 vertices. A degree of a vertex in a simple graph has to be less than the number of vertices. Cannot be 7, so it is not a degree sequence, not a graphic sequence. Is the sequence 0, 1, 2, 3, 4 graphic? As we have seen in the previous slide, you cannot have all vertices with distinct degrees in a simple graph. Okay, so in a 5 vertex graph, a degree 4 vertex would be adjacent to every other vertex. We cannot have a vertex of degree 0. So therefore, no, it cannot be a graphic sequence. Now, these were some simple cases where we could directly state from observation where a particular sequence of non-negative integers, a degree sequence of a graph or not. However, we need a proper theorem to check whether a given sequence of non-negative integers which satisfies all the basic conditions is a degree sequence of a simple graph or not. So for that we have the Havel-Hakimi theorem. So it states that a degree sequence d1, d2 up to dn is graphic only if the degree sequence that results if we delete one vertex, okay, if the resulting graph is also graphic, then we can say that the original sequence is also graphic. Okay, so we assume here that all the degrees have been sorted in a descending order. So D1 is greater than or equal to D2 is greater than or equal to up to so on is greater than or equal to Dn. They are all sorted in descending order, and this sequence is graphic if and only if the degree sequence D2 minus 1, D3 minus 1, D1 plus 1 minus 1. Now, why do we have to subtract 1 from all these vertices? This is because we are deleting a vertex D1. When we are deleting a vertex, we are automatically deleting all the edges incident to that vertex. So, because the degree of this vertex is D1, therefore D1 edges will get deleted. And because we have sorted it in descending order, 1 degree will get subtracted from the next D1 vertices. Okay, so let's take a look at the proper steps that we have to follow to check whether a degree sequence or sequence of non-negative integers is graphic. So given a sequence of degrees, sort the sequence so that it is ordered as D1, D2 up to Dn with D1 greater than or equal to D2 greater than or equal to so on up to greater than or equal to Dn. So they are in descending order. Delete the first term D1 and subtract 1 from the next D1 terms, leaving the sequence D2 minus 1, D3 minus 1, and D1 plus 1 minus 1. And the remaining terms from D1 plus 2 up to Dn will be as it is. Now from here there are two possibilities, two options. First, the sequence has n minus 1 terms. If they are not all in the range 0 to n minus 2, we immediately give up. The sequence we got is not graphic. That is, we'll check the basic necessary conditions that we had checked before. All the vertices cannot have a distinct degree, etc. Now, second possibility, second option is you have to go back and repeat this operation, but you stop when you get a sequence of all zeros. Okay, so this will be much simpler to understand with an example. So let's take the example of a sequence 5, 5, 5, 4, 2, 1, 1, 1. Okay, delete 5 and subtract 1 from the next 5 numbers. Okay, so if we delete 5 over here and we subtract 1, it will be 4, 4, third one 4, it will become 3, then this will become 1, and this will become 0. So next 5 vertices are affected, right? Now we again sort it to a descending order and 4, 4, 3, 1, 1, 1, 0. Again, we'll perform the same step over here. We'll delete 4 and we'll subtract 1 from 4, 1 from 3. Next 4 vertices will be affected, and we'll again sort the resulting degree sequence. So it gets sorted to 3, 2, 1, 0, 0, 0. Again, we'll perform the same step over here. We'll delete 3 and we'll subtract 1 from this, which will become 1. We'll subtract 1 from this will become 0. And we have to subtract 1 from this will become -1. Okay, so one obvious condition for a sequence to be graphic is no vertex can have a negative degree. Okay, so therefore this sequence is not graphic. Let's let's test the sequence 3 3 3 3 2. Delete 3 and subtract 1 from the next three numbers. So we get 3 minus 1, 3 minus 1, 3 minus 1 and 2. So we get all 2's. Delete 2 and subtract 1 from the next two numbers. Therefore we get 2 minus 1, 2 minus 1 and 2. Sort it to 2 1 1. Delete 2 and subtract 1 from the next two numbers. We get 1 minus 1, 1 minus 1 which is 0 0. So finally we stop here and we conclude that this sequence is graphic.